Hello students, so let's continue with the properties of adjoint or the theorems related to adjoint. Okay, first theorem is if A be any given matrix, square matrix of order n, then A into adjoint of A, this is matrix multiplication, will give you adjoint of A into A. Okay, this will be same as this, and determinant of A into identity matrix. So you will get this result. Okay, you can prove this by using some matrix A. Okay, so verification you can do. Now a square matrix. Next is singular matrix. Singular. Okay, singular matrix means your determinant should be equal to 0. When you get a determinant of a square matrix equal to 0, then that matrix is called singular. Non-singular means determinant of a square matrix is not equal to 0. Okay. Next theorem, if A and B are non-singular matrices of same order, then AB and BA are also non-singular matrices of the same order. So non-singular means A is determinant of A is not equal to 0 and determinant of B is not equal to 0. Okay, then you will get AB determinant not equal to 0 and BA determinant not equal to 0. Next theorem, the determinant of the product of matrices is equal to product of their respective determinants. Okay, that is determinant of A into B is given by determinant of A to determinant of B, where A and B are square matrices of same order. So you can prove this using some A and B matrix. Okay, you can find out the product and then take the determinant, and then you have to take determinant of A and determinant of B, and then you have to multiply. So you'll get it equal to this. Okay, next is if E is any square matrix of order n, then determinant of adjoint of A, okay, is equal to determinant of A raised to n minus 1. Okay, square matrix of order n is given. So suppose you have, say, A be the matrix of order n. Okay, order is 3, suppose. Okay, then this result will be adjoint of A square. Okay, so this is like a property. Okay, next is a square matrix A is invertible if and only if A is non-singular matrix. So we can find the inverse of a matrix if and only if that matrix is non-singular. Okay, and from this theorem we have derived a formula to find A inverse. So to find A inverse, okay, 1 upon determinant of A into adjoint of A. So this is the formula to find A inverse. Okay, and you can find A inverse if and only if provided your determinant is not equal to 0, that is A is non-singular. Okay, now there is one more method to find A inverse. Okay, suppose a question is given, say your matrix is 2 3 1 2. Okay, this is your matrix given, and it satisfies the equation, say a square minus 4a plus I equal to 0, where I is 2 by 2 identity matrix and O, that is this, is 0 matrix. Now using the equation you have to find A inverse. Now here they have asked to find A inverse using this equation. Okay, so sometimes they ask to show that this is equal to 0. So this is equal to 0 you can show by using, you have to find first a square, okay, then you have to multiply here a, and then you have to add this 3 and you will get 0. Okay, let's find out a inverse using this equation. So start with that equation, you have to multiply by a inverse. So multiplying by a inverse throughout this equation, okay, you can, a square you can write it as a into a, right? So a inverse, or you can write here a inverse multiplying 4 into a inverse and I into a inverse. Now we know that a into a inverse is I, right? So a into a inverse is I minus 4 into I plus I into a inverse will be a inverse. Okay, so a into I is a minus 4I plus a inverse. Now you have to find a inverse, that is you have to take this numbers that side, so it will be 4I minus a. Now put values of I, that is I is your identity matrix, so 4 0 0 4 minus your a matrix, that is 2 3 1 2. So finally you will get 4 minus 2 2, 0 minus 1 1, 0 minus 3, 4 minus 2 2. So this is your a inverse. Okay, so this becomes your a inverse. This is another way to find a inverse, that is using equation, using matrix, okay, using determinant. If they say, then it is a adjoint method. Okay, let's solve one more question. If suppose a matrix is given, and B matrix is given, okay, you have to verify AB inverse equal to B inverse A inverse. Okay, this you have to verify. So first you have to find product AB, that is matrix multiplication. So 2 3 and 1 minus 1, so this will be 2 into 1 2, 3 into minus 1 minus 3, 2 into minus 4, 3 into 3 9, 1 into 1 1, minus plus 4, minus 2, minus 12. So this is minus 1 5 5 and minus 14. Okay, so this is your AB. Now to find AB inverse, you have to make use of adjoint. So adjoint of AB will be what? So I am writing here directly AB inverse equal to 1 upon determinant of AB into adjoint of AB, right? So first you find out determinant of AB. Determinant of AB is 14 minus 25, right? So this is minus 11. So we got determinant of AB which is not equal to 0, so it is a non-singular matrix. So you can find out A inverse. A inverse exists. Now you find out adjoint of AB. Adjoint of AB is transpose of cofactor matrix, right? So adjoint of AB, transpose of, first you write down the cofactor matrix of AB. So this will be you have to interchange this as 14 minus 1, and here sign change, you have to change the sign, transpose. So transpose of this will be, no, this is direct, right? This is direct. When you take cofactors, then you have to take the transpose. This is direct. So this is your adjoint of AB. Now put values in this. So 1 upon minus 11 into adjoint of AB, minus 14 minus 5, 5 and 1, minus 1. Okay, so this is your AB inverse. Now you find out B inverse and A inverse. So B inverse will be 1 upon determinant of B. Determinant of B, 1 into 3, 3. 3 minus 2, that is 1. Then adjoint will be 3, 1, 1, 2. Okay, this becomes B inverse. A inverse is minus 8 minus 3, so minus 11, and minus 4, 2, minus 3, minus 1. This two you have to multiply using matrix multiplication. So this will be 3 B inverse, A inverse. So it's minus 1 upon 11, minus 12, minus 2, minus 14, then minus 9, 4, so minus 5, then minus 4, minus 1, minus 5, minus 3 plus 2, minus 1. So we are getting